Right, guys, I want to talk about not damped oscillations, forced oscillations, and in particular, when forced oscillations lead to resonance. So, when I describe resonance, what I'm talking about is that situation where the amplitude of oscillations increases wildly, I'd say. You know, I said the example of when you're on the bus and you see the pole in particular getting vibrated more at one particular frequency. So this is a situation here that you might use to try and describe forced oscillations. So what's going on? You've got a spring here. Okay, so this spring has got a mass on the end of it, and if you just displace the mass a little bit, and it'll naturally oscillate. Okay, that's what will naturally happen. As well as that though, the end of the spring here is itself being forced to move up and down at a particular frequency. This is like a rotating like gear. So the end of this cable here is going round. So at this point where it's furthest away, the spring is highest, and then as it gets around to say here, it's you know, the cable's closest, so the spring is lower. So if that's going around at a particular frequency, this is moving up and down at a particular frequency. So this is what's going on here. So I'm calling X the distance of, well, it's the mass I'm talking about really, but I'm saying X is the distance of the mass from its initial position, okay? Whereas Y is the distance of the end of the spring from its initial position, all right? So then, if using that then, we would say, using Newton's second law, we'd say, you know, force equals, I'm just going to say this is positive, this direction here, positive. We'd say force equals mass times acceleration. So the force going this way, down, mg. Oh, I haven't even said that, have I? E. Oh, T, the two things that I want. Right, there's mg, that force, and there's that force tension there. So mg minus T is equal to mass times acceleration. Okay, so that's what we've got there. Right, now, what do I mean when I say tension? We're going to use Hooke's law. So we're going to use, and I don't mean lambda x over L, I just mean T equals kx. So if we have mg minus T times the extension, now I say x, I mean extension. What is the extension of the spring? The extension of the spring is how much it's extended from its initial unstretched position. So that is E and plus X minus Y. I'm just going to explain that now. E plus X minus Y. Here's our spring over here. It's got initial length L and it's got initial extension E. So that is when I put the mass mg on the end of the spring, it stretches a little bit by E from what it was unstretched. And on that then, I could say, if I put a force of T0 there, I could say T0 is equal to K times E of Hooke's law, or T0 minus mg equals 0. In other words, Ke is equal to mg. I've just done that over there, just in order to get that there. Did I say K and I wrote T, or did I say T? I don't know, but I'm talking about K, that same K there in terms of K times extension, right? So anyway, is equal to d2x with dt squared. Now, so just be clear on what's happened on this spring here. An unstretched spring is caused to stretch a little bit by having the mass put on the end of it. That's E. So that's one bit of extension. Then it's displaced a little bit, which is X. So the total displacement is E plus X. But then we're going to take away Y, because that's how much it's gone down from where it started. So this distance X might not necessarily represent the extension of the spring, might it? Because some of it might be how much it's been moved down or the end of it's being moved down from there. So this is what we've got there. I'm conscious of written this rubbish. But there we've got mg minus k into e plus x minus y is equal to m d2x plus dt squared. Right. So we've got mg minus ke minus kx plus ky is equal to m d2x plus dt squared. Okay, that we've just said that's naught. So mg minus ke is naught. Alright, so this is what we've got. I'm going to write it the right way around. M d2x plus dt squared. Move that over there. Plus kx is equal to ky. Okay. Now, let me do one last thing. Let me just divide by m. So if I have d2x plus dt squared plus k over m x is equal to k over m y. Right, now, that is exactly what we want. I'm just going to rename this. Let me rename this k over m. Let me write it like this. d2 x plus dt squared plus some positive number, yeah. I'm going to call that positive number omega squared. X is equal to omega squared y. Okay, now, that is an equation that represents for us forced harmonic motion. Okay, now in this case, that y, that extension of the end of the spring, we're going to have that moving, not at a constant or anything. We're going to have it going round because of the way we've set it up. This y is sometimes, well, it's going up and down with simple harmonic motion. The way this is going round, it's got a different frequency, right? But I'm going to say this. I'm going to say that the frequency of this y is it's going round at y equals sine omega t. So this is how y is some amplitude a sine omega t at the frequency omega, capital omega, that this is going round at. So this gear is going round at a frequency of capital omega, and it's causing the end of the spring to move up and down with frequency capital omega. So let me rewrite this for the last time then. I've got d2x per dt squared plus omega squared x is equal to a omega squared sine omega t capital omega. Now that is the differential equation that we're going to solve. Right, I'm going to try and solve it a bit quick, but it's not, you know, it's nothing different to what we've been solving recently. What's the complementary function? We know the complementary function. The complementary function is x equals a sine omega t plus b cos omega t. Yes, nice one. Okay, what about a particular integral? For a particular integral then, we're going to use the right-hand side. So look at the right-hand side. What will we use for a particular integral for the right-hand side? Well, we'll use, you know, it's just some number times by sine omega t. So we're going to use some numbers times by that there, so times by, you know, the form of this. So let's do it with p sine omega t plus q cos omega t. Okay, right, now, what do we need to do there? Then we just need to substitute this particular integral into this differential equation and see what happens. So in order to do that then, we'll need to work out x dot and x double dot. Okay, so we've got, can you see that? Yeah, x equals p sine omega t plus q cos omega t. dx plus dt is equal to, let's differentiate that, p omega cos omega t minus q omega sine omega t. What about d2x plus dt squared? Let's work that out. Minus p omega squared sine omega t minus q omega squared cos omega t. All right. And now let's sub it into the original differential equation. We've got d2x with t squared. So minus p omega squared sine omega t minus q omega squared cos omega t plus omega squared times x. So plus omega squared p sine omega t plus omega squared q cos omega t is equal to, and I've nearly finished here, a omega squared sine omega t. Right, what do we have to do here? All we have to do here is equate coefficients. Okay, so what's the coefficients of sine on the left-hand side? What's the coefficients of sine on the right-hand side? What's the coefficients of cos on the left-hand side? What's the coefficients of cos on the right-hand side? I'm just going to write them out. So, of sine omega t, the coefficients on the left-hand side, we've got minus p omega squared plus p omega squared is equal to a omega squared. Right, so that tells you what p is. So p is omega squared over omega squared minus omega squared. So it's omega squared over omega squared minus omega squared. And let's do the same for cos omega t. What's the coefficients there? We've got minus q omega squared plus q omega squared is equal to naught. So q is naught. Yes. Right, so we've got the answer. We've got the answer for the displacement of the bob as it's moving up and down. It is x equals, put the two together, the complementary function and the particular integral. We've got a sine omega t plus b cos omega t plus, and then it's p sine big omega t. So it's omega squared over omega squared minus omega squared sine omega t. And that is it. Now, like that's the answer. Right. Now, that's brilliant, because that describes for us resonance. That is a function that demonstrates resonance when we were to plot it. Look at it. It's got two parts. It's got this part here, which is just normal simple harmonic motion, and then it's got this part here, which is the forced frequency. Now, what you can see is, as you change the forcing frequency, as you change omega, you change the amplitude of these oscillations here. These will dominate if this here were to be really large. What would make that really large? Well, what would make it larger than anything would be if omega was equal to omega. So that is to say, if you were to make the system vibrate at the natural frequency of the system, then you'd have what we call resonance. Then the amplitude of the oscillations would increase wildly, and you get this phenomenon that we know. Now, you know, in this here, you're not allowed to have omega equal omega, are you? Because that doesn't work. And we sort of know that anyway, because what the actual differential equation that you'd solve in that case would be this. It would have been d2x per dt squared plus, I'm just looking at the previous one before, omega squared x is equal to a omega squared sine omega t. Now, right, the point is here that your complementary function is a sine omega t plus b cos omega t. Okay, I'm just getting that from before, what I was talking about before. So your complementary function is a sine omega t plus b cos omega t. The particular integral can't be p sine little omega t plus q sine cos little omega t, because that's already in the complementary function. So what you'd have t times the complementary function, and that would be the point, is that then as time increases, the amplitude of the oscillations gets bigger and bigger and bigger, and that's what we mean by resonance. And that's just all I wanted to say there, was a little explanation of that phenomenon. Okay, nice one, guys.